Okay, hope you can all hear me okay. So thank you very much for coming to this presentation, taking time out of your busy evening. And as the wonderful introduction, which you must have put quite a bit of time researching because you pulled from various different sources, I can tell. So as was talking to you today about fusion energy, and I geared this presentation hopefully to the appropriate level for the crowd, and I'll try to step through some sections here, like what is fusion energy, how do we make fusion energy, what are the technologies associated with getting high temperature plasma, which is the fourth state of matter, and maybe according to all of our minds is how close is this really? Are we getting any closer? Is it always 30 years away? So hopefully by the end of the presentation, you'll have some further insights on all of these things. The research group that I work on is in the plasma physics program in the applied physics department. Our website is there. You're welcome to look at that. And every once in a while, we hold public events with tours and things like that. So keep your eyes open for announcements. Probably the next one will be around Climate Week in September. We usually do it at that time. So with that, I'll be going through these sections. And the last section is a little bit shorter, but I'd like to spend most of my time on kind of the big picture of fusion energy. How we get there, and when are we going to get there? Okay, so let's go. So the motivation for working on fusion is multiple. There's overall a broad desire for us to move away from high carbon-producing technologies and into more energy technologies that are going to allow us without the negative consequences of greenhouse gas. Furthermore, going for hydrocarbons attaches us to some other states that might not have the best interests of this country at heart. And so these are both very strong pulls. As you can see in the little graph there, the need for energy is going to be increasing. And of course, physics and engineering has a really strong role in solving this problem. This slide was from, I made this slide about a year ago, and even since then, things have changed. So I'm going to modify the slide for you. And now there's another pull in here. Maybe machine data centers and all. You're seeing a lot of additional investment in energy technologies simply to power data centers. Okay, so new rationales come around, and I think that there's a broad acceptance across the whole country that more energy in a way that doesn't harm the environment is obviously pursuing that. And there are many, many technologies that can get us there, and the work that I do is to try and have fusion be one of those technologies that can contribute to this overall cycle. So fundamentally, where's this energy coming from? Well, inside of every nucleus, which is inside of every atom, which is inside of every piece of stuff that we're all made, there's potential for energy to be liberated. This is a plot of the energy stored in the nucleus per nucleon, in there, either a proton or a neutron. And as you can see, there's maximum stored energy in the unfortunate atom called iron. So you can't really squeeze iron, but if you happen to be lighter than iron or heavier than iron, there's a path to change your atomic species and get energy out and pop up into here. So for fission with conventional nuclear power, you take a very heavy atom and you split it, traversing down this way. That's pictured here. And then the fusion process takes a very light atom and then combines it. Both of these processes liberate tremendous amounts of energy from the nucleus. So both of them are actually or different forms of fire. So when you take a chemical reaction, which you might expect from burning, this creates or something like that. To make fusion happen, you actually need to get the temperatures way, 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 way higher. And in fact, we don't even use Celsius or Fahrenheit. We use something called electron volt. Electron volt is 10,000 of these degrees. So you need to get to something like 20 million degrees, or to something like 2 kilovolts. The sun can just use gravity. It can pull all those particles together. It can create high pressure just by being big and fat and carrying all that energy into the center. So we don't have that on Earth. So on Earth, we have to devise really elaborate machines and devices that can make high. One of the motivations for going for fusion is that there's significantly less fuel required. And this is actually true of both conventional fission power and fusion power. both of them are liberating energy from the nucleus. And like I said, that nucleus has just a tremendous amount of energy. You tend to use a unit called a mega electron volt to define that energy, which is 1,000,000 electron volts. And remember, 1 electron volt is 10,000 degrees. So there's really just a ton of energy stored inside every one of these reactions. So because there's so much energy per reaction, you can get to the situation where very little fuel is necessary because your reactor produces so much energy. So I grabbed these two little cartoons from the internet. I just Googled fission fuel and fusion fuel. It's about the same because this is a pellet. It's probably like, maybe 10 grams or something like that. Is like a ton of coal or 120 gallons of oil. 1 kilogram of fusion fuel makes 6 million kilograms of natural gas and 10,000 kilograms of coal. So for both of these systems, the fuel input is not the biggest thing. It's actually a device. And so the cost of your plant for both fission and fusion is really about the cost of building the machine. Once you've built the machine, what's in there becomes less of a part of the overall economic situation. Now, fusion in fact, has some other challenges that I'll get into about the fuel that it needs, but even there, because there's so little of it, it ends up not being the dominant cost that we need. So it's all about the cost needed. You should think about that as like investment needed to build a big thing or build a thing. More in that framework. Another reason that people are interested in fusion as compared to fission is that fusion has significantly less radioactive byproducts. I think we know that they're both executing nuclear reactions, so they're both, at the time that the energy is being produced, producing some radioactivity. You don't want to be near an operating either of these kinds. But what's different between fission and fusion is that because fusion is taking the light atoms and turning the issue with radiation in fusion is really only there immediately while the reactions are taking place, and then it's called residual activation, which quickly decays away. So you can look at the plot here, and you can see that actually it depends but if we made it out of steel, then after 100 years you get to a low level of radiation. If you made your plant out of something fancy called vanadium, after 10 years, pretty, or maybe that's 20, low level of radiation. Or you can go even fancier, and maybe this is something like a third generation plant using a fancy material called copper, and that one never activates. So you can get into a situation where for all of these different kind of flavors of making fusion plants, if you wait not that long, facilities in the United States that can already take this level of activation, they're called Class C waste facilities in New Mexico and things like that. So this kind of basis was possible. So this is one of the main advantages that you see in principle of going for fusion as compared to just continuing on with fission. Okay, so people consider fusion for this slide, so it's all nice and pithy. It's clean, there's no emissions, there's no long-lived, high-level radioactive waste. So I told you there's some radioactivity, but it's short-lived, low-level. What it means by that is that it's a plant, so you actually put it somewhere, and then it produces energy for you there. It's safe in the sense that there's no risk, I'll probably know what it is later, and it's scalable in the sense that if you need double the energy of it, then you build double the plants, triple the plants. So ultimately, it's actually really quite amazing. It's a device that you put somewhere and it produces energy with not too much fuel, as with fission, but without all the other concerns that people do. I think it has a role to play in our ecosystem of energy, but fusion is the next generation and more advanced form with many fewer of the drawbacks of fission. And secure here, this is meant to say that our fuel sources are not subject to the whims of other nations. Here's a little cartoon of what the reaction looks like. So we take, it comes as a gas, but it can be heavier based on how many neutrons are attached in here. So this is something called a deuteron. This is something called, they're different isotopes of hydrogen. So they're different flavors of hydrogen. And then these come together in some magical box, and they produce energy, byproduct of the helium. And then here's your neutron. Most of the energy is actually carried in this neutron. This neutron would then go and go somewhere and then produce steam and then produce a turbine to rotate. And then this helium ends up being recycled into the reaction and maintain the temperature that you need. We'll go into that in a second. Okay. So for me, there's also a really interesting technique that makes fusion happen. So back in the 1940s and 50s, all of these different technologies were exploding. Very quickly progressed through these three different technologies. Uncontrolled fission, nuclear weapons, played a role in the Second World War, as we all know. Uncontrolled fusion nuclear weapons. These are what we call hydrogen bombs. Also, still to this day are an important part of our national consciousness. And things were done within a span of 10 or 13 years or something like that. But we never figured out this. No one back then to this day, we still haven't exploited controlled fusion power, fusion energy. So even from the point of view of a technical grand challenge, I think it's, for me, a very obvious gap in the ability of our species to do an exciting stuff. So I sort of alluded to this a little bit. All of these developments happened in a very short time. And so we went from weapons in the 50s, military applications of controlled fission in the submarine program, which then grew into the aircraft carrier program, and all done in a very, very short time. So why didn't we get fusion a few years later, right? There was still quite a big push. It's just really hard. How are we going to build a box around this thing that allows the conditions to be created without melting itself? We'll talk about that in the rest of the presentation. So how do we control the reaction? How do we get the high temperature conditions? How do we overcome the high capital output? So this was actually not fully appreciated, but because the conditions needed are harder to get, it tends to cost more to test a thing. And so you end up not being able to test as many things because you're limited in how much money you can spend per need R&D. So we'll spend the rest of the presentation kind of exploring why there wasn't fusion in the 1960s. Okay, so to summarize this section, what's fusion and why bother? It's a process by which you merge two nuclei and you produce tremendous amounts of energy per reaction. And so to do this, ability for clean, firm, stable, scalable, and secure energy in the plant that you put somewhere. But we're still not at the ability where, if somebody went to a company and said, buy me a fusion plant, okay, here it is. We're not there yet. It's still really hard. There's still R&D challenges that we're trying to overcome. Part 2, how? What are the approaches? So we'll spend some time discussing a few different ways conceptually that this can happen, but there's a clear concepts or approaches that have received more interest, more quickly, also more investment. So those paths are further along. And in my personal opinion, we have many approaches that are not fully supporting even the ones that are ahead. So it's not really so important to be trying really hard. So we'll talk in this presentation about maybe 3 or 4 different approaches, but just keep in mind there are more than what I'm describing. Okay, they all have the same goal though. All these different approaches to fusion are ultimately trying to do the same thing, and they can all be measured against things in terms of what condition they're achieving. The most obvious one is the temperature that you get. So you need to be, this is a cross-section, and you'll see they're all characterized by a unit, kilo-electron volt. Electron volt is 100,000 degrees. Kilo-electron volt is like 10 million degrees, and you can be 100 million degrees. So that's quite a high energy, and so you're definitely dealing with something called plasma, and we'll talk about that in the next slide. This is a cross-section. To get a significant number of reactions, you actually need a high density of particles, and if both of these happen together, then that means you have high pressure. So you need to have high temperature, high density, and high pressure in a box that hasn't melted itself. So how are you going to do that? So as you increase the temperature, hopefully this is all coming back to us from school, you go from solid, liquid to gas, but then maybe we didn't learn about this one, I don't know. If you keep going and keep heating up the gas, then you actually take the constituent atom. The atoms are made of nuclei and does its own thing. It's floating as its own soup. So you have a soup of electrons and a soup of ions, and they each exist together, and it's like kind of like oil and water, or maybe I don't know, two different types of fluid, and they're just hanging out together. And as they move in relation to one another, they produce electrical currents, and they react to magnetic fields. So that's plasma. After the blood plasma, because somebody looked at the plasma and said, oh, it kind of looks like blood plasma. So that's why now there's two things that are called plasma, which are in somebody's mind back in the 1910s. Plasmas are all around you, so you can see them in neon signs. We don't see that very often. And then in the aurora, which maybe you've seen if you're going to the northern lights. So all of these things are different plasmas that are all around you, and if you like astronomy, a great many things you see in the universe are actually plasmas hanging out in there. Now, unfortunately, these are all actually 1,000 times at least colder than the temperature of plasma. So these plasmas are not producing neutrons or anything like that. They're just too cold. But they're on a path. They're still probably like 10 degrees, but not hot enough. They're not 10 million degrees or 100 million degrees. Okay. So I should actually put the fusion. Gravity is the best approach to fusion. That works really well. If you're the sun, you can just use that. Magnetic bottles or magnetic fusion has very, very powerful electromagnets that guide the plasma. We'll talk about that. And the first one we're going to talk about is inertial fusion. So inertial fusion is the most plasma, and to compress, shove together the fuel to a very high density and temperature. But there are other ways you can create the inertial fusion. I'm focusing on a few of the approaches right now. So we'll focus on laser fusion for the next few slides. I'll just say, for my personal experience and competence inside of the house, so I just don't have as much experience with the inertial fusion. I think it's very interesting. The movies that I'm about to show you, I think, is cool, but I probably won't have like the depth of knowledge. If you have questions about the laser fusion, you can probably have somebody come and give you a presentation about laser fusion in the future. Okay, so I did grab some slides from some of the leading experimental facilities in laser fusion, and if you heard this weapons program based at Lawrence Livermore National Laboratory. And very big kudos to them. They were the first group that actually achieved what we'll call a burning plasma. And into the fuel was so much that it actually produced more energy coming out of the fusion than was coming in through itself. Heated itself up. So it was much more than just the laser going on in there. The reaction itself was sustained, and it produced ignition. It's not just the laser or the whatever got the plasma hot. reacted and made itself yet more hot. And so that was the process of ignition. It's a very important milestone for the fusion program that happened for over 10 years, really doing science, understanding what was going on, and improving their system, and ultimately getting. Okay, so the National Laser is the largest and most energetic laser. So here are some football teams, some of which no longer reside in their scientific facility, and it has 192 lasers that can produce really just numbers that are out of this world. 200 terawatts of power, which is 1,000 times more than the entire electrical grid, are coming down those football fields and being focused into a very, very small area. So the lasers enter a capsule here, and we'll discuss in the next slide what goes on inside this capsule. And the fusion fuel that they're heating is this little guy here. It's like a BB. So the BB is full of the fuel, tritium and deuterium. And the lasers, see it? Maybe go a little larger. Maybe I'll get the laser for you on this one. There it is. That laser. The power of the laser, I forget the ratio. I want to say like at least 100 or 1,000. So it just gets smashed by that laser energy. It's actually more the room, the outside of this chamber, and that chamber is made usually of a very high atomic number, but different materials. The X-rays then bathe the fuel in an intense radiation field. That radiation process, and here you can imagine it has to be done very precisely, or else, oops, your fuel might, kind of go inside. And so that needs to happen in just the right way to actually get the conditions to go through. And that this approach, let me just jump back a few slides, just like approximately what happens inside of a nuclear weapon. So that's why that program is, in the end, ultimately trying to understand the physics of what the nuclear weapon is doing, and for a really justified and good end, it's to avoid testing. So the program that came after the test ban. So instead of testing nuclear weapons, which gives some people indigestion, the idea was to use a laser to mimic the conditions, allow our understanding to proceed without having to do the testing. That's a little backstory. And now I have for you, it's kind of jumping a little bit. It looks okay. So then you see the energy from the laser turning into X-ray. Like I said, I don't really work on this, so I don't really know what's going on. But look at the shape of this thing. For a while, it's sort of like a diamond, and then a diamond, and then it's circular again. So all sorts of work is going into do the simulations, compare the two, and adjust. And for me, it's really a triumph of science and technology. That cycle, a virtuous cycle, until they got this thing to actually work the way it was approximately expected to work. It was a very long challenge for the team in there, and really represents the best of science and technology. The fusion, 3 megajoule, good. That's a net win. Up to 5 megajoules have been produced. However, However, the system itself is not very efficient, nor was it designed to be efficient. It was designed to get the job done in this particular condition. And so you can see it took 300 megajoules. I don't have a slide about that, but this laser can only fire a few times a day because it takes a long time to cool. And for this to be economic production, it needs to fire many, many times, several times per second. There's both efficiency gains needed and temporal repetition gains needed. However, this program is now demonstrates. So if you have approximately this amount of energy into approximately this kind of chamber, you can foresee something like this. And I'll just point out that the process of fusion is extremely nonlinear. So you can get, for example, 3, 5, not that much change, which also means that if you increase the energy of the laser by 10%, so I think for the next several years, you will see continual good news out of this program and continual more fusion produced, because even small improvements in the performance of the laser non-linearly boost you up in this program. Okay, magnetic bottles. That's the other side of the program. And it tends to be that the folks who do magnetic fusion from those who do laser fusion, because the conditions going on in here are quite different than the conditions in the magnetic bottles, and they both have different pros and cons. This is a picture from The Economist, nice and simple. Big blue magnets, yellow plasma inside the fusion chamber. Of course, the systems are more complex than this, but to zeroth order, that's about right. There's a set of. You might also see that there's 2 broad types of magnetic bottles that have received the most interest. The tokamak, the accelerator, designed in the United States. And the characteristic difference between these two, this one looks the same all the way. They're both donuts. They're both different types of donuts, and so I always think of them as donuts. Okay, why are they donuts? Of the particles. So that particle in there sees the magnetic field and it zips around it in a never-ending circle. So what you want to do is basically have the magnetic fields bite their own tail so that the particles stay in this ring. Acceleration in this direction, they're just hanging out in there, going in circles, confined by the magnetic field. So if you had like a magnetic field touching the wall, that would be like a leaky point where your particles would leak. It'd be hard to get the temperature up because the plasma would get cold. B, wherever it touches would melt. So that's bad. So you want the field lines, they're called magnetic field lines, to just go circles and circles and circles and never touch the wall. So both of these do that. This one does so with the property of symmetry, so with the twist. And the twist is basically here has to do naturally. We can get into that later. Okay, so these are 2 different concepts. And you can see here's a nice little XKCD comic. Okay, so in the laser fusion, the fuel is kind of pre-confined because it's this little bead and shoot. In the magnetic fusion approach, here the plasma is like pre-confined in a ring, but something's got to heat it up. So fusion approaches to heat up plasmas in magnetic fusion, and this is another area of research and development, which is like, what's the best way to heat this? It would be 100 million degrees. You got to shoot energy in there to heat it up to that temperature. So actually these all have pretty nice analogies. If you all have electric heaters in your rooms because it's a cold day, what happens in there? You drive a current through a piece of whatever and it gets hot through the process of ohmic heating. So that same process happens in plasma. You run a current through the plasma, it produces thermal heat, and it heats up the plasma. This works pretty well up until a point, but you usually need to boost it with something else. The conventional way to heat plasma to high temperature are twofold. There's radio frequency heating, and this is basically a microwave. You use all sorts of different frequencies for plasma, but not quite 2.45. But it's the same basic idea. You shoot in waves, they produce oscillations of the particles inside, heats it up. The second one is beams. So you can actually shoot a particle beam, and it's sort of like a particle accelerator attached to a plasma. And you shoot in some high energy particles, and it heats up the plasma. So both of these things need to be there's usually, and that for the magnetic fusion approach is like the equivalent of a laser in terms of your energy balance. So you want to compare the fusion coming out to the amount of energy coming in through your radio frequency wave or your ohmic or what have you. So there is a facility in England called JET, Joint European Torus. And this is a tokamak flavor facility, so the one that looks the same all the way around. And it produced the record for fusion energy in terms of actual joules. So that experiment produced very high power, but for a short time. So the energy was 3 megajoule. This was less intense, but longer for 5 or 6 seconds. And so that was a lot of energy overall. And so the amounts of energies that were produced in this experiment, something like 69 megajoules at the record, something like 59 megajoules. And just again, on this comment of it being pretty nonlinear, the difference between these two were probably pretty modest. Like I boosted you up a lot. That's enough to power 50,000 homes for a second. I Googled that because I didn't know how much power a home might take. So now I know. It's about 800 kilojoules. Actually, kilowatts. Where you live, actually, I was looking at different regions of the country. They each have different each utility has its own average number. That was an aside. Nonetheless, a lot of homes for not very long, for a second. But this had a rough 69 megajoules coming out, but more energy than that was going into the waves and the new beam. So this experiment, while scientifically extremely productive, didn't quite get to where it wanted to get in terms of more energy out than in. But it got really close. To get to that break-even point, it was just wasn't quite there. Almost. Okay, second movie. So I showed you the movie of the laser because it happens in like a nanosecond or whatever. So you saw the simulation. Here's a real movie of the tokamak because everything happens over a longer period of time. So slowed down, but you get a little bit of the flavor of what's going on here. I think this is a really cool movie. Hopefully it doesn't jitter too much on you. So you're going to see streamers that go around, and that's actually cold particles that are emitting more, but it allows you to see the topology of what's happening in there. Right, so let's go. So you're looking at both sides of that torus, end on to the donut beams. So you usually don't see the middle of a plasma for your eyes. If you had X-ray vision, it'd be super bright. You'd see all the X-rays. But for regular visible light, it's too energetic. So it's like you know what it is? It's the dark saber in Star Wars. The center is too hot to see. Now, why can't I get my cursor back? All right, here we go again. I'm not going to talk too much about my research in this presentation, but I spend a lot of time thinking about why that looks the way it does. Zero order, why it didn't do slightly different things. So, laser had a dramatic advance of the ignition break-even thing in California. Very good for the laser program. Magnet has an equally interesting and important advance, in my opinion, at almost the same time, which is the demonstration of a twice powerful magnet. So magnetic fusion is sort of like the most obvious thing you can think of. If you make a twice thing in there, in the device can get twice better because you just made a better magnet. All the other things were held equal. The one startup company in Massachusetts actually figured out how to take. Sorry, I lost my cursor. Where's my cursor? Still a large-scale magnet that was able to get to something like 20 Tesla. So a typical magnet that you might have made quite powerful. Why do you care about the magnetic field? So basically, those little orbits, they are kind of like how big your box is, right? Because you've got one orbit here, its buddy is over here, its buddy is over there. So if you can maybe have a certain size magnetic field, maybe your device is 10 orbits left. And that's going to set sort of how hot it can get, because each of these orbits talk to one another. And so that sets ultimately how much of a temperature you get between this experiment. If you increase the magnetic field by double, those orbits shrink by half. So now all of a sudden you get all the orbits in your box, all of a sudden it gets twice as hot because you've got that many more orbit separation in there. So for the same size box, if you double the field, all of a sudden it's twice. That's not actually what you do. You take something that would be twice as big and you make it half as big, or I guess you know what I mean. So from twice the size to once the size, and because that's the linear dimension, you go from something that had a volume of 2, which is 8, to something that had a volume of 1. And usually the cost is like the volume. So all of a sudden, with this doubling of the magnetic field, you've gone to something almost order of magnitude cheap. So that's really what makes everyone very excited about the magnetic approach now, that you can double the magnetic field, halve the size of the box approximately, or drop the cost approximately. There's many other things going on, but that is pretty close to why everyone's excited about this. Okay, this section. How? You need a hot plasma. How are you going to get a hot plasma? Basically, powerful lasers or powerful magnets. Next section. When? Start with the story of the price of oil, because I think it tells you a lot about the history of the fusion program. So the value of energy is basically changes over time. At some periods of time, prominence in our society. In the 70s, the oil crisis, some of you know this, had a very profound effect on our society, and so that triggered a flood of alternative energies. And then I'll tell you that there was a period for fusion while the oil price was low. I have a second resurgence, not only because of the original rise of the price of oil, which did happen, didn't sustain actually, but also because of, so for both of these reasons, energy became more valuable, and so then again we had a second era for fusion development. So in the early, the fusion budget in the early days, slack is the fusion budget, it looked like it was on a good track. Things were happening, experiments were being built, like that jet fusion. The price of oil fell, nobody felt like clean energy was that important, and the experiments didn't produce the same, the physics results that were being hoped for. So instead of these optimistic paths, which might look a little bit more like the space program did, when that was being done back 10 years before this, the actual fell. Okay? So in this period from 1990s to 2000, the budgets were pretty low. And so when the budgets are very low, when nothing much is happening, you get into this view, which at the time is always, is very reasonable, which is that fusion is never happening. It's always 30 years away. And the real reason that is because nobody's working on it. Okay, not very many people are working on it. Not very much is happening. It's always going to be in the future because we're not getting the job done. We're not getting close. The story of NIF is different because of the weapons work. So that's not the ignition facility. That's happened during this period, which I call the doldrums. So effectively, all nations realized they couldn't get to the scale needed for fusion on their own. So they banded together and formed the multinational ITER project. And the United States, for political reasons, fusion was seen as a topic we could work together on because it was so far away it didn't have any importance, okay, in 1985. Along the way, other nations joined the party, and so the EU, there's many parties in ITER. So this is something that happens. So I don't want to characterize the 1990s and 2000s as nothing happening, but this thing that happened is that a bunch of really smart people continued to work at the problem and understand the fundamental physics. So during this time, the field of plasma, which is really all about how to understand what's happening inside the box, continued to develop. Computation continued to develop. A lot of scientific effort was put towards it, and now we have a much more comprehensive suite of predictive tools that can tell you, okay, if my box is 2 meters and I put 2 megawatts in, how hot is it going to get? So there is a path to answer that question. There's always uncertainties, but you can do that now and get an answer for that. So for this, I have a third movie, which is why this is hard, why that computation is not straightforward. So here you're seeing fluctuations. So this is the onset of a wave, and then poof, this kind of jumped. Spreads, and it becomes this soup, this turbulent mess. So what you're really asking when you're asking how hot, it's very much like a cauldron of boiling water. You're asking how hot is the top of the kettle versus the bottom. Okay, how does it transport through this turbulent fluid? It can be done, but it's tricky. So that's the sort of question of plasma. This is a turbulent mass. It's basically a swirling fire cloud. Okay, so then in the 2020s, things happened that improved the outlook of fusion. The societal pull is back through the importance of extreme weather and climate change. New technologies, like the magnet, offered a far less path, and the scientific basis was improved, as I showed on the last slide. And this manifests in, for example, the achievement of the laser program that I showed you earlier, and the magnet doubling. So all of these things have produced a climate where there's a much better perception for how close we are to fusion energy, and much more support. And I'll tell you a few metrics for that. So the emergence of the private sector, startups in fusion, is one of the indications that all of these things are coming into alignment and progress is happening more quickly. There is now an explosion of companies, and they're all different approaches. By the way, I looked at this plot. This plot came from the Fusion Industry Report. If any of you are scientists or teaching science, never make a plot like this. Look, the x-axis changes. This is a very short period of time. This is a very long period of time. It looks much more like a hockey stick, okay? But they made the plot in this way. It's okay. So I'll ask them why they did that. So nonetheless, nonetheless, the important point is here. In the last 5 years, there's now 40 or something companies. But it shows you that there's a lot of interest and a lot of different approaches being pursued. Ultimately, some consolidation will happen in the sector, and we'll have fewer. Really, there's an ideal number of concepts to move forward. It's probably closer to 5 than where we are now. Some companies is too few, but maybe like a dozen or something like that. Okay, and then here's another plot that I had to update in the recent years. In Fusion. This one has the appropriate x-axis. That's the same throughout. And so you see the hockey stick. So there's the hockey stick of investment. And so now the number, I think, to quote is 7 billion. It might be closer to 8 in the last, or 7.5, even since this plot was made. And the investment is continuing. Comment that it might have only been because interest rates were low. Certainly interest rates being low, long-term investment, but the investment is continuing in the harsher interest rate environment. So I think that's a positive sign for the field overall. So our future level of success, basically, or sorry, I'd say it the other way, the future level of investment and whether this curve continues depends on now the companies actually doing things. So the companies will raise money with certain milestones, which might be like build a powerful magnet or show a high temperature plasma or something like that. So these are now the sorts of things that these can be judged on. And so my answer to the when question is really a how much question. How much money has been put in? If not very much money is put in, it's going to take a long time. If a lot of money is put in, it's going to go faster. So it's not the direct answer you might be looking for, but I'll do a little more on that question as we go. So here's history. They're all wannabes for SpaceX, and there's a great many of them. And I think it's overall a very exciting thing. I'm running a little low on time, so I'll tell you quickly here. So these are all venture capital sponsored. There's a wide range of approaches. I want to connect this to the beginning of the presentation. So you can see magnetic confinement is like half, inertial confinement a quarter, and muon catalyzed fusion. We won't talk about that. And then in terms of specifics, stellarator, laser, another kind of tokamak. So that's, gives you a big chunk of what's being pursued. So those are already like the leading contenders. So that's why I focus on those in this presentation. Typical fusion company roadmap. They all kind of look the same, and that's for good reason. Technology demonstration. And so for this particular, I'm showing one from a specific company called Commonwealth Fusion Systems. For this technology demonstration was a power magnet, the high field magnet that I showed a few slides ago. Roadmaps then typically move on to a energy gain demonstration device. But that's the usually the next step. And then third step is the device that delivers power to the grid. For a Series A, this might be a Series A or a Series B in terms of investment language. And demonstration devices tend to cost about $1 billion pressures, so it's difficult to get that in like a cheaper package than $1 billion, unfortunately. And then something more for the power plant. The approach might vary. That's still the development path. Enabling R&D, demonstration device, power plant. And so when are each of these going to happen? If how each of these steps are taken and how much money the companies can raise. So the companies are the ones that are going to try and do this for the next 10 years, and we'll see how many get to what state, how much investment. Demonstration device, say for this geometry, doesn't work, doesn't get hot, and so then that approach is abandoned. And the other thing I want to add is that there's enabling R&D that the public sector has to do to support these concepts go go the rest of the way. So there's many common technologies that all of these will need, and so it's really the role of the public. Okay, timeline. So this is something, again, you can find in the Fusion Industry Report. When a company will deliver power to the grid, there seems to be a preponderance of 2030 to 2035. I'll tell you my personal opinion. For this, requires significantly more money than what's presently been invested. So that hockey stick to $7 billion is not going to get us to this target. And so for this to happen, the investment has to go into the companies to actually execute the roadmap in a timely manner, and into the public sector to execute this roadmap. Right now, I think there's a handful, 2 or 3, that are funded at the level that they're on track. Maybe, in my opinion, not to get to this one, but to maybe this one. They're capitalized to be on the path to that goal, but they're not going to get there with their current investment to see this kind of time frame. So, furthermore, each of these steps take time. So, for example, let's just take this one. From the test facility to the plant will take at least 5 years, even if you knew exactly what you were going to do, because you have to build all the different components and things like that. So when is all this going to happen? My comment to the audience is to keep track of the money, keep track of the investment flowing into these companies. How many companies are getting that level of investment, and how many companies have deployed their demonstration device successfully? So the demonstration device should see in the next 5 to 10 years or less. And so that's already, like, to the left of this chart. And so you'll see who is on the path to get to this step in the 2030s. So I wanted to show you one demo. So this is a company, again, from Commonwealth Fusion Systems. And so you can see this is the sort of scale of a demonstration. It kind of looks like a factory. This is a picture of what the plant is going to look like. So that's the demonstration, one-to-one. Person in the basement. And then this is a factory. It's actually the structure over here that's building the components for the demonstration device. So I can't tell you exactly when this demonstration device is going to turn on. Okay, ITER. I started with ITER. ITER's still there. ITER's continuing. So this is what happened to ITER in the intervening time. This is really a nuclear reactor at this point. So it's got all the supporting structures, large main facility here. And so most of the components have been designed and delivered and made by the members. However, there have been issues in assembly caused delay in this sort of time frame over here. Unfortunately, there have been delays at that project. This is the picture advertising the presentation. It's being put in, and so these components are there, but they're still sort of getting it together. Okay, my last point. We're not the only country in the game. And in particular, I want to approximately double what the US is investing into this program. And many of their plans are not even public. So there's definitely an international race. There's opportunity, in particular among allies. And it's a very dynamic and interesting time in this program, especially as all these different countries are going for it either in partnership. And yeah, so that's, I think, all I wanted to say. What are the bottlenecks industry in the United States? They all need to make demonstration devices. Demonstration devices cost about $1 billion, and money equals time. So if you invest more quickly, you'll get there faster. Sorry, if you invest, if we don't invest, it's another 30 years. You've got to actually spend the money to get to where you need to get. And with that, I think I'll conclude. I'm going to skip the clinic. I took a little bit of time, so just get to the end here. And so with that, thank you very much for your attention and participation, and I'll take questions.